The question is simple. Could we build a real quantum computer? The answer is yes. And also no, and maybe. It depends on what you mean by real. If you mean a machine that uses quantum mechanics to do something, then we've already done it. We have them now. They sit in labs, cooled to temperatures colder than deep space. Scientists can run programs on them. They exist, but if you mean a real quantum computer, the way people talk about them online, the kind that will break all encryption and design new miracle drugs overnight, then no. We are not there. We are not even close. And the path from here to there is full of problems so hard they make rocket science look like basic arithmetic. This isn't a story about a single breakthrough. It's a story about a slow, difficult, and incredibly expensive crawl towards a machine that might change everything. Or it might just end up being a very specialized tool for a few specific problems. The truth is, nobody knows for sure. So let's talk about what's really going on. Let's talk about the physics, the engineering, and the monumental challenges that stand in the way. First, we need to understand what we're trying to build. What makes a quantum computer different from the computer or phone you're using right now? Your computer is built on bits. A bit is a simple switch. It can be either a 0 or a 1, on or off. That's it. All the complexity of your digital world, from videos to video games, is built from billions of these simple switches. They are reliable and predictable. A quantum computer uses something called a qubit. A qubit is not a simple switch. It can be a 0, it can be a 1, but it can also be both at the same time. This is a core idea in quantum mechanics called superposition. Think of a spinning coin. While it's in the air, it's not heads and it's not tails. It's in a state of both possibilities. Only when it lands, when we measure it, does it collapse into a definite state of either heads or tails. A qubit is like that spinning coin. It exists in a fuzzy cloud of probability, a combination of 0 and 1 until you look at it. This ability to be multiple things at once is powerful. If you have 2 classical bits, you can have 4 possible combinations, 0, 1, 10, or 11. But you can only represent one of these at a time. With 2 qubits, because of superposition, you can represent all 4 of those combinations simultaneously. With 3 qubits, you represent 8 combinations. With 4, you get 16. The number of possibilities doubles with every qubit you add, which is 300 qubits. You could represent more combinations than there are atoms in the known universe. This is where the incredible computational power comes from. A quantum computer isn't just faster because it does things in parallel. It explores a vast landscape of possible answers all at once. There's a second quantum trick that's just as important. It's called entanglement. You can link 2 qubits together in a special way. They become part of the same quantum state. After that, no matter how far apart you take them, they are still connected. If you measure one qubit and find it's a 0, you instantly know the other one is a 1, or whatever the entangled state dictates. As Einstein called this spooky action at a distance, because it seemed to violate the rule that nothing can travel faster than light. But it's real. It's been proven again and again. Entanglement allows qubits to correlate with each other, creating complex, multidimensional computational spaces that are impossible for a classical computer to simulate. The final piece of the puzzle is called interference. This is the real magic. A quantum computer in a calculation is like dropping a pebble in a pond. It creates waves. Superposition lets you create many waves at once. Entanglement links these waves together. Then, you carefully choreograph these waves so that they interfere with each other. The waves corresponding to the wrong answers cancel each other out. The waves corresponding to the right answer reinforce each other, becoming stronger. At the end of the calculation, you measure the results, and if you've designed your algorithm correctly, the most probable thing you'll see is the wave that has been amplified, the right answer. So, a real quantum computer is a device that can create and control a large number of qubits, keep them in a state of superposition, entangle them with each other, and use interference to find answers to specific problems. That's the blueprint. Now, where are we today? We are in what experts call the NISQ era. That stands for Noisy Intermediate Scale Quantum. Let's break that down. Intermediate scale means we have machines with a decent number of qubits, from a few dozen to over 1,000. That sounds like a lot, but remember the exponential scaling. It's a start. Noisy is the important word. And it's the word that separates today's machines from the dream machines of the future. Noise is the great enemy of quantum computing. A qubit in its delicate state of superposition is like a soap bubble. The slightest disturbance from the outside world can pop it. A tiny change in temperature, a stray magnetic field, a vibration, even a single photon bumping into it can cause the qubit to lose its quantum state. This is called decoherence. It's the process of the qubit forgetting. It was both a 0 and a 1 and collapsing into a plain old 0 or 1, just like a classical bit. When that happens, your calculation is ruined. Everything is a source of noise. The materials the chip is made of. The control wire is sending signals to the qubits, the equipment used to measure them. It's an endless battle against the universe, which seems to want nothing more than to look at our qubits and collapse them. To fight this, the leading quantum computers are kept in huge, elaborate refrigerators called dilution cryostats. They look like giant gold-plated chandeliers. They cool the quantum chips down to millikelvin temperatures, just a sliver of a degree above absolute zero. At these temperatures, atoms barely move, which reduces thermal noise dramatically. But it doesn't eliminate it. So, the machines we have today are noisy, the qubits decohere very quickly, often in a tiny fraction of a second. This means you can only run very short programs before the errors pile up and the result is just garbage. We have demonstrated quantum supremacy, where a quantum computer performed a very specific, carefully designed calculation that would be practically impossible for even the biggest supercomputer. As Google did this with their Sycamore chip, it was a major milestone, but the calculation itself was useless. It was designed only to prove that the quantum computer could do something a classical computer couldn't. It didn't solve any real-world problem. This brings us to the hard part. The gap between a noisy 1000 qubit NISQ machine and a truly useful, fault-tolerant quantum computer is not a gap. It's a chasm. It's a series of monumental engineering and physics problems that we are only just beginning to figure out how to solve. The first big problem is the qubit itself. There is no standard way to build a qubit. It's a bit like the early days of classical computers, with vacuum tubes, relays, and transistors all competing. Right now, there's a zoo of different approaches, each with its own strengths and weaknesses. The two leading contenders are superconducting qubits and trapped ions. Superconducting qubits are what Google, IBM, and Rigetti use. They are tiny circuits of superconducting metal etched onto a silicon chip. They are fast. You can perform operations on them very quickly, but they are also very sensitive to noise and have short coherence times. They are also relatively large, which makes scaling up a challenge. Trapped ions, used by companies like IonQ and Quantinuum, take a completely different approach. They use individual atoms, charged ions, as their qubits. They hold these atoms suspended in a vacuum using electromagnetic fields and then manipulate their quantum states with precisely aimed lasers. These qubits are incredibly stable and have very long coherence times, sometimes lasting for minutes. The operations are also very accurate. The downside is that they are slow. The process of using lasers to nudge individual atoms is much slower than sending electronic pulses to a superconducting circuit. There are other less mature technologies too. Photonic qubits use single particles of light, photons, as qubits. Their big advantage is that they don't need to be kept super cold. They can work at room temperature. But building the gates that make photons interact in the right way is extremely difficult. Then there are silicon spin qubits, which try to use the quantum property of an electron spin inside a standard silicon transistor. This is appealing because we could potentially leverage the massive, mature semiconductor industry to manufacture them. But controlling single electron spins is fiendishly difficult. Right now, nobody knows which of these technologies, if any, will win out. It might be that different types of qubits are better for different types of problems. Or it could be that a completely new approach we haven't even thought of will prove to be the best. The point is, we haven't even settled on the basic building block yet. The second, and arguably biggest, problem is how to deal with noise and errors. Even if we perfect one of these qubit technologies, they will never be perfect. There will always be noise. There will always be errors. A qubit might accidentally flip from a 0 to a 1. Its phase might drift. These errors will always be a part of quantum computing. So how do we build a reliable computer out of unreliable parts? The answer is quantum error correction. This is probably the most important concept for the future of quantum computing. The idea is borrowed from classical computing. Your computer's memory also has errors, but they are corrected so you never see them. The way it's done classically is with redundancy. You store a bit 3 times. If you want to store a 0, you store 0. If one bit flips due to an error, you might read 10. The system can then see that the majority of the bits are 0, assume that was the intended value, and correct the error. Quantum error correction is vastly more complicated. You can't just copy a qubit. The act of measuring a qubit to copy its state destroys the superposition, which is the whole point. This is called the no-cloning theorem. So you have to be clever. Quantum error correction codes spread the information of a single ideal qubit across many physical qubits. These physical qubits are entangled in a very specific way. You don't measure the qubits themselves, but you perform measurements on the group to check for syndromes, which are signs that an error has occurred. These syndrome measurements tell you what kind of error happened and where, without ever looking at the actual quantum information stored in the qubits. You can then apply an operation to fix the error. This creates what is called a logical qubit. A logical qubit is a robust, error-corrected qubit made from many noisy physical qubits. It's the quantum equivalent of that redundant zero. It can survive for much longer and perform many more operations than a single physical qubit ever could. This is the path to truly powerful, fault-tolerant quantum computers. But the cost is staggering. The overhead, the number of physical qubits you need to make one logical qubit, is huge. Early estimates suggested thousands, or even tens of thousands, of physical qubits would be needed for a single logical qubit. Recent progress has brought that number down, but it's still likely to be in the hundreds. So, to build a quantum computer with just a few thousand logical qubits, which is what you might need to solve a truly hard problem like breaking encryption, you would need a machine with millions of physical qubits. And all of those millions of qubits would need to be controlled and measured with incredible precision. This brings us to the third massive problem: scaling. Building a chip with 1,000,000 qubits is not just a matter of making today's chips bigger. It presents a whole new set of challenges. Think about a superconducting quantum computer. Each qubit needs at least a couple of control wires running to it to send microwave pulses. 1,000,000 qubits would mean millions of wires. How do you run millions of wires from room temperature electronics down into a cryostat that's close to absolute zero without introducing a massive amount of heat and noise? This is known as the wiring problem, and it's a nightmare. Then you have to measure all those qubits. You need sophisticated electronics to read out the state of every qubit at the end of the calculation. Doing that for 1,000,000 qubits at once is a data handling challenge on a colossal scale. And you need to do all of this while keeping the error rates of the physical qubits extremely low. Quantum error correction only works if the underlying physical error rate is below a certain threshold. If your qubits are too noisy to begin with, adding more of them just adds more noise, and the error correction scheme fails. We are just now getting to the point where the best qubits are good enough to start making error correction work. It's a cascading series of problems. To get to a useful machine, you need logical qubits. To get logical qubits, you need quantum error correction. For error correction to work, you need a huge number of very high-quality physical qubits. And to build a machine with a huge number of high-quality physical qubits, you need to solve immense challenges in wiring, control, and fabrication. It's a mountain with many false summits. Let's say we solve all that. Let's say in 20 or 30 years, we have a fault-tolerant quantum computer with a few thousand logical qubits. What do we do with it? This is the fourth major challenge: software and algorithms. A quantum computer is not a universally faster computer. It will not speed up your email or make your video games run better. It's a specialized machine that is only good at certain types of problems. The most famous quantum algorithm is Shor's algorithm. It's an algorithm for factoring large numbers. This is the one that gets all the attention because the security of most of the internet relies on the fact that it's incredibly hard for classical computers to factor large numbers. A sufficiently large quantum computer running Shor's algorithm could, in theory, break this encryption. This is a real threat, and a lot of work is going into developing quantum-resistant cryptography to prepare for it. Another well-known algorithm is Grover's algorithm, which provides a significant speed-up for searching unstructured databases. But for most of the problems we solve with computers every day, we don't have a good quantum algorithm. Finding new quantum algorithms is a very active area of research, but it's hard. You have to think in a completely different way in terms of superposition, entanglement, and interference. It's not intuitive. So beyond code breaking, what are the problems a real quantum computer would be good for? The most promising area is in simulation, particularly quantum chemistry and material science. Your nature is fundamentally quantum mechanical. The way molecules bond, the way proteins fold, the way new materials behave, these are all quantum phenomena. Trying to simulate these processes on a classical computer is incredibly hard. The complexity grows exponentially. But for a quantum computer, it's a natural fit. As Richard Feynman, one of the fathers of the idea, said, "Nature isn't classical, damn it, and if you want to make a simulation of nature, you'd better make it quantum mechanical." A fault-tolerant quantum computer could simulate new drug molecules to see how they interact with the body, drastically speeding up pharmaceutical research. It could help design new catalysts to create fertilizers with less energy, which could have a massive impact on world hunger and climate change. And it could allow us to design new materials for better batteries, more efficient solar cells, or room temperature superconductors. These are the kinds of world-changing problems that motivate the huge investment in this field. Another area is optimization. These are problems where you have to find the best possible solution from an enormous number of possibilities. Things like optimizing shipping routes for a global logistics company, or managing an investment portfolio, or designing the airflow over an airplane wing. For some of these problems, quantum computers might be able to explore the vast space of possible solutions more efficiently and find better answers than any classical computer could. So, where does this leave us? The journey to a real quantum computer is a marathon, not a sprint. We are still in the early stages. The current NISQ machines are like the first vacuum tube computers of the 1940s. They are massive, unreliable, difficult to program, and can only perform very simple tasks. But they are a crucial first step. We are learning how to build and control quantum systems. We are testing the basic principles of quantum error correction. We are developing the first primitive quantum algorithms. The path forward is one of slow, incremental progress. It's about getting the physical error rates of qubits lower and lower. It's about figuring out how to pack more and more high-quality qubits onto a chip. It's about solving the scaling and wiring problems. It's about demonstrating the first real logical qubit, then 2, then 10. It's a process of relentless engineering. There will not be a single moment where quantum computing suddenly works. It will be a gradual process of these machines becoming more powerful and more reliable year by year. So, could we build a real quantum computer? Yes, we have the physics right. The theory is sound. We know what we need to build. We are building the first prototypes now, but the engineering challenge is perhaps the most difficult humanity has ever faced. It requires manipulating matter at the level of single atoms and single particles of light with a precision that is almost unimaginable. It will take time, probably decades, and the final machine might not look anything like what we imagine today. But the effort is not just about the final goal. Along the way, we are pushing the boundaries of what we know about material science, information theory, and the fundamental nature of reality itself. We are learning to speak the language of the quantum world, and that by itself is a remarkable thing. The answer to the question is that we are building it, right now. One impossibly cold, incredibly fragile, and genuinely amazing qubit at a time.